Okay. So good morning and happy Friday. Another weekend is coming, and today I'll be finishing up on decision trees and talking about ensembles, and then showing you a demonstration of ensembles. And if we don't get to that today, we'll do the balance of that on Monday. In addition, on Monday, I'll be the one giving the presentation, but I'll be talking about how to give an effective presentation. And so I also have the final project posted. Oh, you know what? I'm a little bit mismatched. My wife is in the Bay Area for the next week and a half. It's been a half a week so far. So it's just my daughter and me. So I have a lot of stuff on my mind managing everything um, um, at the home site. All right. Let's see. Ensembles, something I'm forgetting. All right. Well, before we begin, the usual administrative bits. Something I'm forgetting. Oh, yes, yes. Final exam. Final exam. That's what I'm forgetting. So I'll bring up the PDF for the final exam after we finish this module on decision trees, and we can talk about what it's about as well as what I'm looking for. Okay. All right. So we have one class on Monday left. It's been, wow, 15 weeks so far, just about. It went by faster than I thought it would. All right. So where we last left off, we talked about decision trees, and we saw an example of a decision tree from scikit-learn in the Jupyter Notebook. And to draw your memory, we have a method for supervised learning. So we have our unknown target function in our anatomy of a learner, and the label set assigned by this unknown target function for your in-sample data, it's discrete. And so this could be two-way, like we talked about in perceptron learning algorithm, +1, -1, approve or deny, or it can be an arbitrary k-way with a discrete so-called class label. We also talked about, just that I mentioned the names, the two major algorithms, and these aren't the only ones for decision tree learning algorithm that searches through the space of hypotheses for that final best hypothesis that most closely matches the labeling action of our unknown target function. And so the ID3, iterative deepening 3, was the original method, and then the improvement by Ross Quinlan, very interesting person, is the improvement. But this isn't the only set of decision tree algorithms. There are umpteen many variations of them. And so my goal in this class is to give you sort of the two major flavors of decision tree, and then leave it to you to look through the literature and documentation for APIs for the many, many dozens of nuanced takes and variations on the base decision tree induction algorithm. And so the benefit of these types of learning models, decision trees in particular, is that they're interpretable. Once the learning algorithm halts or finishes, and you have a new out-of-sample instance, you send it through your classifier. And if, for example, in the mortgage approval problem, it comes out, no, this person should be denied the mortgage, you can now go back through your model and read off how it arrived upon that decision. So that's useful for a large variety of applications. This is all to jar your memories. Okay, and so we start out with a set of label input pairs, and we said our data points are vector instantiations in feature space in D dimensions, and we have associated with each in-sample point, our historical data, we have a ground truth label assigned by unknown target function. And so among the label set, we can enumerate them. There are k many labels for a k-way classification in an arbitrary supervised learning problem. Any questions? No? Jar your memory. All right. And so how do you do this? Well, when your learning algorithm is running, you're training your model or fitting your model to data. Now we can say that. You take your in-sample data and you build a tree. And that tree consists of a bunch of nodes, and each node represents a statistical test. And the result of that statistical test is either a two-way decision, pass or fail, or a k-way decision. Now, when you take your in-sample points, it creates this tree using the notional best nodes or best tests. And the result of this test is for that set of data points that you sent to the node to be partitioned. So they're chopped up into subgroups. And this partitioning happens again and again and again in this tree data structure until they come to rest at the bottom, the so-called leaf nodes. You have nowhere else to go. And the idea then is to produce partitions that are very homogeneous in the number, in the examples that are collected in ultimately the leaf nodes at the bottom. Does that make sense? Now, when I say homogeneous, I mean homogeneous in their class label. And so the numeracy of the different class labels represented by those subsets that come to rest at the leaves of the tree at the bottom is not very many alternatives, i.e. there's a lot of information. Does that make sense? Any questions? All right. And so when you get a new input, you take this new input in vector format and you send it down the tree that has been built by our learning algorithm. And that new input comes to rest at a leaf node. And then in the model, you predict that particular label, a y hat, representing the majority of the labels of the training data that came to rest in the leaf nodes as a result of your training phase when your learning algorithm halted. Does that make sense? Okay. And so this idea of how you search for the best tree is the goal of the decision tree induction or learning algorithm. Okay, so we have our vector value data, and imagine our data set had big N, many examples in D-dimensional feature space, and each vector instantiation, we said, is a collection of random variables, the outcomes of those variables. And as such, we can look at all of the different values. For example, years in residence can take on, or annual salary can take on. And so if we collect all of those values in this notation, which I think I flubbed a little bit last time, we have the ith data instance, and that I indexes over which data point it is. And then for each one, we have a jth attribute. And so here we see x hat, and that x hat is vector notation, the unit vector, and that represents that feature value or that projection of that d-dimensional point on that particular axis. And so the axis that measures a particular feature value, like years in residence axis or annual salary axis, that's going to be one of these features. Now, if you look at all of these values of a particular attribute, you can count them. And we can list them as a set, which is what happens here in this notation. Big XL, wrong pen, is the set of unique values that the jth attribute or the jth variable can take on. Does that make sense? Any questions? No? All right, to jar your memories. So let's continue on with our decision trees. And for this statistical test, we can have two types of tests. One is a two-way test of the sort pass-fail, and another is a k-way test. And so let's imagine we had something that was real valued, like annual salary or years in residence, and we know all of those unique values that particular variable can take on. Well, a test we could make is asking the question, does that particular attribute, is its value greater than some particular instance or instantiation of value, like is annual salary greater than 24,000, or is it less than or equal to that value, less than or equal to 24,000? Does that make sense? Now, when you take your data set, whether it's an out of sample data point or your in sample historical training data, some of your vectors for that particular test, for that attribute within the vector, some of those instances, those data points are going to fail the test. You set them aside in one group. Some are going to pass that test. You set them aside in another group. And so this idea of classification takes your out of sample data, your new data point, applies those tests corresponding to each one of the nodes, and this data point then makes its way down the tree. If you pass the test, you go down the left-hand branch of the node to the next node in the tree. If you fail that test, you go down the right-hand branch. Now, if you're a classification problem, classification problems don't have a categorical data don't have a notion of pass and fail, right? You have categories like cat, dog, truck. And so for categorical variables, when you test those attributes, that's where the K-way test comes in. And in that case, it's not greater than or less than equal to. It's is it equal to each one of these categories that this categorical variable can take on. Does that make sense? Any questions? All right. So this is an example of a decision tree, and this is sort of an oldie but goodie from the literature. And let's imagine we had a vector instantiation, 4 dimensions for our features. And the first feature was the outlook feature that talks about the weather condition. The second one was the temperature. The third one is humidity. And the fourth one is wind speed. And each one of these are categorical. Now, that's in this example. You could absolutely have real valued temperatures and real valued humidities and wind speeds. Now, this is an example of a decision tree. And let's imagine we had these nodes, and each node for these categorical variables, each one of these attributes, corresponded to a K-way test. And so for the outlook, let's imagine the outlook could be sunny, could be overcast, could be rainy, okay? So you have a 3-way test. And for some of the vector instantiations of this 4-dimensional feature space or points in 4 dimensions, some are going to pass the test for sunny, some points are going to pass the test for overcast, and some are going to pass the test for outlook equals rain. So with this, you take your original in-sample data and you apply this test. It's going to partition your data points into 3 subsets. Now, it doesn't matter how many are in each subset. It could be balanced, it could be highly skewed towards one or the other, or you could have no instances in a particular subset. What matters is that when you induce this partitioning, the resulting label applied by the unknown target function is going to have some distribution. And what you're enterprising to do is to make that distribution as labels as homogeneous as possible, i.e. not many different alternatives. Does that make sense? Yeah? All right. And so our next test, humidity, has 2 levels as a categorical variable, high and normal, and wind speed has strong or weak. Now, the label is a binary label, categorical, yes or no, or you could equally say +1 or -1. But what this label is asking you is, should you go out and play tennis? Yes or no? Now, of course, you might ask, why do you need a classifier to tell you whether you should play tennis? Just humor me. It doesn't have to make practical sense. But you can imagine if this were a medical data set and you're trying to decide if you should schedule someone for an MRI. So you could induce a similar type of thing from an enormous medical database and use this to determine the series of questions that the physicians ask their patients and whether or not they should apply certain tests. Any questions? No? All right. And so the idea then is, imagine if we had some new out of sample data, X sub nu, and you'll notice it has an instantiation of our 4 variables, outlook, temperature, humidity, and wind. So we send this new input, this out of sample point, down our tree, imagining this tree were the one that was built. Outlook is sunny, so it pursues this left-handmost branch. And then it comes to the humidity test. Humidity is high, so it pursues this branch. And then it comes to rest in this leaf node. And imagining the majority label was no, then you'd say, okay, this thing is saying or predicting no for this tennis variable. So you shouldn't go play tennis during these conditions. Does that make sense? Okay. And so if we look at this tree, one of the things we notice is if we look at all of the positive examples, these yes labels, if we traverse a root to leaf path for each one of these yes conditions, so outlook is sunny, humidity is normal, yes, go play tennis. Outlook is overcast, yes, go play tennis. Outlook is rainy, the wind speed is weak, yes, go play tennis. So for all of the yes majority class labels for these root nodes, we can actually come up with a logical expression equivalent for this particular classifier. And so if we do that, well, each one of those paths we traverse represents a conjunction or an anding of all of the conditions associated with passing each of these tests. And we take each alternative, each individual path is ORed together, a disjunction. And so what this particular tree in the previous slide represents is the following logical fluent. Outlook is sunny and humidity is normal. If that's true, or the outlook is overcast, if that's true, or if the outlook is rainy and the wind speed is weak, then this logical expression directly describes the scheme that you employ prescribed by this particular tree that was induced from the data or built from the data. Does that make sense? And so whether you interpret it directly from the graph data structure or tree, or you find a logical expression that encodes the equivalent structure of the tree, now you can read off what happens. So you can imagine in the non-categorical case, the real value case, like the mortgage approval problem, it'll say if your years in residence is greater than 8.5 and your annual salary is greater than, I don't know, $42,000 a year, then yes, you're approved for a mortgage. Does that make sense? And that's immensely useful, this interpretability of these models, especially for things that are highly regulated, like mortgage denial, right? There are federal rules in place for that, for historical reasons of bias in lending. Okay. Any questions? No? And so when are decision trees useful? Now, not all models are useful for all types of data. And so one of the things you learn in a typical machine learning class is when you apply certain tools, right? The right tools for the right job. You wouldn't use a rubber mallet to hammer in nails while building a house. I mean, you could, but it's not going to be very effective. Same thing for these machine learning models. Now, certainly a decision tree is for supervised learning, right? We know that at this juncture, but within supervised learning problems, these discrete label sets, they're very useful for certain types of data. So certainly if you can describe your data as attribute values, salary equals some number, or outlook equals sunny, rainy, etc. If you have a system that can be described by the ORing together of various conditions, should I apply this MRI intervention? Should I apply this experimental drug, for example? If you have a discrete set of outputs, well, that's important because of how they work. Namely, your label is discrete, your label set that alludes to the supervised learning nature of a decision tree. If your data set has possible errors in it, decision trees can correct for that because they use this idea of majority when they determine the class labels. Okay, that's kind of nice. If your training data has missing attributes, decision trees can handle that quite well. They just employ some attribute that works. And in many cases, you can get to a class label through different pathways through the tree. Does that make sense? Okay. So we won't expand on that aspect in machine learning models or with models about which model is more appropriate for which pathologies in your data set. But I just want to make you aware that this choice is not arbitrary, and that would be the subject of a machine learning course, or more so would belong in that course. Okay, so let's get to the crux of the matter, get to our learning algorithm, how you create these trees from the data. And so this idea of search, we wanted, because it's supervised learning, an algorithm that's going to search through all of the trees, the collection of nodes, and their ordering from root down to leaf that is best. And so we said best for supervised learning means most closely aligns with the labeling action of our unknown target function. And so we need then a definition for the statistical test, this selection. And in the case of best or most closely aligned with the unknown target function, we do that by making the label sets for that subset of partitioned in sample points as close as possible, that majority label as close as possible to what is there assigned by the unknown target function. Does that make sense? Oh. Any questions? All right. And so let's take a look at where our entropy comes in. And we're going to use this idea of information gain. And what we'll see is that information gain talks about when you partition your data into subsets, and then you take those subsets and you partition those into smaller subsets, how you partition them should result in an increase in information. And we said information is a reduction in entropy. So we want to find partitions on values and selections of attributes to partition on such that the resulting subsets are lower and lower in entropy, lower in disorder, have more information. And that information is going to be measured as the homogeneity of the resulting class label for the subset, the majority class label. Does that make sense? Any questions? No? And so, for example, suppose we have a set of label instance pairs. And in the binary case, we have the positive instances, those are the +1 labels. And we have the -1 instances, those are the -1 labels. And so if we take all of our ground truth labels, we can look at our proportions and compute a probability of having a particular class label. That's just the number of examples that have the positive label divided by the total size of your data set, and the number of instances that have the negative label divided by the size of your data set. So we can actually compute the entropy in the class labels for some set of data. And that set, in this case, is the entire data set over n many examples. And it's a typical compact notation of a data set in publications. And we do that. There's our entropy. You have minus the probability of the positive labels times the log of the probability of positive, minus the probability of the negative labels times the log of the negative labels. Does that make sense? And so we do this calculation after we choose the splits. We propose them, we score them based on the entropy, and then we choose the one that has the biggest reduction in entropy. Does that make sense? Yeah. All right. And so the so-called information gain, it's really the information, well, it's information gain, but you could also call it the entropy reduction, right? Kind of as synonyms. And so we talk about the information gain associated, I keep grabbing the classroom pen and not my own pen. The information gain for a data set, so here S, this is our data set. And then A is just a notation for the attribute. So this attribute in the mortgage approval problem would be years in residence or the annual salary. And so the first thing you do, you say, okay, I have all my data for the mortgage approval problem, and I'm either going to select years in residence as my attribute or annual salary. And for each choice, you do the following. You take the entropy of the entire data set or the entire set that you're given. And when you take the set, you apply some test based on the attribute, and each attribute has a set of values. So years in residence might have 8 years, 7.5 years, 12 years, and so forth. So for each one of the attributes, you look at all of the values that an attribute can take on, and then you partition your data set into subsets based on that value. So you start out with S, your original data, and you look at an attribute, let's say years in residence, and the resulting values, let's say years in residence is 1, years in residence is 5, years in residence is 8, that's going to result in your original input set of data being partitioned into subsets of data. And so if years of residence was 1, we call this S1. If years in residence was 5, we call this S5. If years in residence was 8, we call this S sub 8. And so in this notation, the subscript represents the individual values that that attribute can take on. And then in these subsets is that subset of the original data that was passed in, S in this case, that subset that satisfies that particular condition. Does that make sense? All right. So what do? We take the entropy in the labels associated with the original data set passed in, and then we subtract from it a different entropy, the expected entropy based on the splits that are possible for this particular attribute. And so here we take the size of that subset, S sub V, and we divide that by the size of the original set, S, and then that's our probability of having a subset SV, right? And then we use that as our probabilistic average, weighting the entropy of that subset. And that's entropy of the labels for those examples in the subset. Does that make sense? And so we have the total entropy, and you could call this the expected entropy of the subsets. Does that make sense? Any questions? No? All right. All right. So the information gain about this label talks about the target function for each of the attributes. And gain, you could think of when we look at information as the number of bits used to represent or count all the alternatives. Information gain is the number of bits that you save when you try to encode the value of the labels for the resulting subsets as a result of that particular partitioning. Does that make sense? Any questions? No? All right. And so in essence, our learning algorithm for decision trees, it's supervised learning, but the learning algorithm searches through the space of all of the possible orderings of these partitioning tests using a score of this information gain. So it wants the biggest decrease in the number of bits, and that biggest decrease is the same as increasing your information, fewer alternatives. Does that make sense? All right. And so ID3, iterative deepening algorithm version 3, and no one really knows what 1 and 2 were. It searches through your hypothesis set, and essentially it takes your data, and this is our example we've been carrying through. We have annual salary on the horizontal axis, years in residence on the vertical axis, and it's basically forming what we call axis parallel splits. When you give a statistical test, your test is based on a particular value your variable takes on, all the values. And what it's asking in the case of real valued is your data set less than or greater than equal to this particular value. And so let's imagine our point cloud that we've been carrying through in this scheme. And let's say we chose years in residence, and we want to have one of the years in residence, okay? Well, this point has a years in residence, that point has a years in residence, all the points have a projection on the vertical axis representing the years in residence. So we want to choose one of those values with which to partition the data. And then from that partition, we subdivide our data set. So here, if we're using years in residence, this green line is the axis parallel split associated with value A, which is this years in residence attribute of that particular data point that this dotted green line pierces. Does that make sense? Any questions? And so our test asks for the years in residence across our original data set, S includes the blue points and the red points, are they greater than A for that attribute, or are they less than equal to A? Now, if we look at this partition of everything below the line, well, that's very homogeneous. They're all red points. Their label is all -1. But if we look above the line, it's heterogeneous, right? They're mixed between the -1 and the +1. Can we do better than this? Okay. So let's take a look at this particular data point, and we're going to look now instead at the salary axis, the salary attribute. And so each one of our data points has a salary value, which is this projection along the horizontal axis. And for this particular point, wait a minute. If we use that to split up our data, partition it, everything that's less than equal to value B, well, they're all -1 labels. That's very homogeneous. There's a lot of information there. Everything that's greater than B for our annual salary feature or attribute, they're all blue, right? So yeah, that matches perfectly. It's ideally homogeneous. Does that make sense? Any questions? And so the information gain will say, for this particular attribute, salary, you're better off because we can get a really good reduction in the number of bits represented. It's more homogeneous if you split on salary than if you split your data based on years in residence. Does that make sense? Any questions? No? All right. And so there's a problem here with ID3. And ID3, it prefers attributes associated with tests that are quote unquote more bushy, right? That's not a technical term. If we have an attribute that has a really large number of values, that is going to be preferred by ID3 because when you have more splits, you have a fixed number of data points. Let's say you had 200 data points, and let's say one attribute had 50 different values. Now, on average, you're going to get about 2 data points per subgroup when you do that split based on these values, right? And so the problem is if you have a more bushy node, it means you have more branches coming out of that node, which means if you're checking, is your value cat? Is it dog? Is it mouse? Is it rabbit? And so forth. The resulting subgroups are going to be, by definition, more homogeneous because you have so many ways to divide this finite data set. Does that make sense? And so one of the problems with ID3 is that it has a bias towards nodes that are more bushy, categorical nodes that have more alternatives. Does that make sense? And so what C4.5 does is it takes this information gain and it penalizes it for bushy nodes. And the idea is to choose nodes that reduce the information gain, but not so because it's very bushy. Does that make sense? And so there's something called the split information criteria. And this is the split information criteria. It takes as an input a set of data points and an attribute, and it computes what looks like the entropy of the resulting partitions when you have your attribute. And so here, I is each of the values, it indexes over each of the values that a variable can take on. And so this is the probability of a data point being that value. And this is the log of that probability. So P of X times log of P of X, that's exactly the entropy. And so what it's doing is it's measuring the split information, how many alternatives you have for this particular variable. And so if you have fewer alternatives, you notice the leading negation, it's going to be a smaller number. If you have more alternatives, it's going to be a bigger number. And so what C4.5 does, it takes your information gain, computes something called a gain ratio, and it uses the split information as a penalty. And so if you have a more bushy node, the denominator is going to be bigger, and this resulting gain ratio is going to be smaller. If you have a less bushy node, fewer alternatives, this information gain is going to be larger. And so what C4.5 does is it takes our ID3 and it makes it more fair. Does that make sense? All right. Any questions? No? All right. And so this is the C4.5, and that was the version of decision trees that I showed you last time. You can also use decision trees to do regression. And so the difference we said between a regression problem and a classification problem, supervised versus, well, they're both supervised. For a regression problem, our class labels are real valued, like temperature, pressure, humidity, and so forth. To turn a decision tree, so-called regression tree, into a regressor, it's still an interpretable model, so that's great. You can have interpretable models for real valued predictors. Our labels are real valued, and the criterion for which variable we split on is no longer information gain. We look at the reduction in variance in this real valued label, depending on which particular attribute you use to do the splitting. Does that make sense? Any questions? And then the prediction, when we travel down the tree, our new out-of-sample data point comes to rest at a leaf node, and then the prediction that you make for it is going to be the average of all of those in-sample points that arrived at the same leaf node. And so it's just like decision trees, But this idea of homogeneity is using variance because it's real values we're trying to predict versus information gain for the regular decision tree, because you can have mixed values, but the label is discrete for supervised learning. Does that make sense? And so if you look in scikit-learn, you'll see regression tree, you'll see decision tree. The decision tree is specifically for supervised learning. The regression tree is for real valued predictors. And the power of these models is not just because they're predictors, but these are interpretable. So if you have any kind of data problem where you want to, after the fact, furnish the rationale behind why an out of sample point was predicted the way it was, these two models will do that for you. Any questions? Does that make sense? Okay. So this humble decision tree, I might say, well, it's really axis parallel splits. Yes. But there's a lot of transformation you can make on points in feature space, changing the geometry in all sorts of interesting ways. And the beautiful part about this is that if your transformation is nonlinear, then instead of axis parallel splits, it's drawing arbitrary shapes, but you only pay the cost of the base level algorithm of axis parallel splits. And that's the so-called kernelized version. And I really hope to teach my version of machine learning some point in the future. We'll see. I've certainly covered that. All right. Any last questions? No? So we'll switch to the other module. And let's first go to the brain hiccups. Go to the final project for a few minutes, and then we'll pivot to ensemble methods. And then I will show you in the Jupyter notebook some of these ensemble methods, as well as correct the error that I had from before with the E out and EN. Okay. So let me bring down the slides. Keep. And let me bring up the PDF. Let me redo the share. Share screen. Let's see. Preview. Share. All right. So this is the final project. And the final project consists of two components. One is the presentation, and the other is the actual project work itself. And so with this, the scenario, and it's open-ended, is that you are on the data science team for a company called SoFi Technologies. SoFi.com is a company, and they're really a tech company, but they're also a finance company, and they focus on personal finance products. And so I'll leave it to you to look on the website at what types of finance products they offer. But at the end of the day, you're going to be making a recommendation to SoFi Technologies. No, I haven't spoken with the company, so this is just purely fictitious scenario. But you're going to be making a recommendation. Excuse me, a recommendation. Sometimes I run out of moisture from my throat. Excuse me. You're going to be making a recommendation to SoFi Technologies for what new financial products they should create to address a problem that you're going to find extracting insights from the data set. And so I made the data set, and this data set corresponds to financial data. And there are lots of financial sources that you can get. LexisNexis is a big one. And these information brokers, they cull lots of data nationally from all sorts of sources. Phone companies do it, and there are special data broker companies that do it. Bloomberg is another one. Moody's is another one. They do that mostly on commercial entities. And so here, you're going to be looking at Worcester, Massachusetts, which has a population of 205, 918 people here, where we are in central Massachusetts. And the data is going to consist of attributes that including annual annual salary, years in residence, age, current debt, monthly housing cost, as well as rental status. And now this rental status is Boolean, true or false, represented as a 1 or a 0. Everything else is real value. Okay. So you're given this, and I direct you to one of many different websites where you can get all sorts of information about the services and amenities available in Worcester, Massachusetts. Now, Worcester is a medium-sized city. There's a lot of commerce in this area in Central Mass, and so there are many services. And these services can include things like social services, transportation services, healthcare, employment services, retail establishments, everything, all of the above. So with this, you're going to be investigating potential products, new products that SoFi Technologies might offer. And so the data set, part of your goal is to identify different customer profiles. So you have to come up with what they are. You have to give them names, and it has to be supported by the data. And so this is an open-ended analysis, but one of the things I specify in the project are what are called in software engineering minimum specs, right? You have to have these particular items. So you have to include cleaning of the data. You have to involve visualization. You have to involve summary statistics. You have to do some sort of analysis looking at relationships. And as we said, correlation is one sort of relationship. The mutual information is another sort of relationship. Mutual information is good for nonlinear relationships. So I'm not going to tell you what these relationships are, but you have to include some analysis of relationships between variables in your data. And you have to involve some other types of analysis, like looking at quartiles or what is an outlier and so forth. And we can talk a little bit more about that on Monday. Your work must involve machine learning methods. I think I said you have to do at least 2. I can't remember what I said. But here I have some hints about what different types of models that we've talked about are good for, right? So you have to involve machine learning methods, and it's your choice. And the important part is why you're choosing what you're choosing and what you're accomplishing to do. And you have to identify populations and subgroups within those that represent this sampling of residents of Worcester, Massachusetts. And of course, if you identify a subgroup, you have to give them a name and describe their characteristics. Does that make sense? Any questions? So yes. Uh-huh. Mm-hmm. Um, you can choose, it's open-ended completely how you present. I will on Monday give my own advice about how to make an effective presentation. But the one constraint I have on the presentation is the time. Well, I have 2 constraints. The time within 10 minutes, all right? So you could choose to use the whole 10 minutes or use less than the 10 minutes. And then everybody will be doing a presentation and recording it. And the only way to fit all of everyone into the 2-hour period given by the registrar for actually delivering the presentation is to select them randomly out of a list, right? So I'll literally bring like a bowl and put strips of paper, and we'll pick randomly who's going to physically present, but everyone's going to record a presentation because I can't force you to have groups. I encourage you to have groups. But if we do have groups, it's like, I think 11 or 12 groups of 2, no more than 2. But if we have individuals, it's going to be 21. And if we have a mixture, it's going to be somewhere between that. And we can't fit that in the 2 hours that we're given for the exam period. Now, for your presentation, aside from the time constraint, it has to have these sections. And I'll talk about what these sections are, but I want to see certain aspects of the problem reflected in your presentation. Did I answer your question? Yes. Sure. Uh-huh. Yes. Ah, wow, that's a great question. It all depends on 2 things, your style and who is your audience, right? Your audience is going to be your peers here. Last year, Dr. Lee Han wanted to see the presentations, but for the most part, your audience is your peers, those who've had the material in the class. And so one of the things I'll talk about on Monday in giving an effective presentation is to know a priori who your audience is. You want to tune it to your audience. Now, of course, there are certain techniques, and I'll talk about it on Monday, that I use. You notice I always begin with a very sparse slide with a lot of pictures, but no words. And that's a technique called shaping. I want to force you to listen to what I'm saying. So I provide the mind's eye for what is going on in the picture and why it's important. Because if there were words all over the screen, you'd just be kind of reading it and not paying attention. You have a finite attention span. And I'll talk about that on Monday as well. And so part of it is your style. The other part is your audience. And you just have to kind of strike the right balance depending on what you believe your audience is and how your style might resonate or not resonate. And so if this were, if it were like open house and you were all high school students, perspectives visiting, I wouldn't give the same type of presentation that I'd give to you after building up all this machinery. And so that's an example of style versus tuning it to your audience. Does that make sense? So it's sort of all of the above, but you choose it based on the statements you want to make and based on your style, what you feel comfortable doing, and based on the audience. Because if at the end of the day, your audience doesn't remember anything what you said, then it's a failed effort. Okay. So I will talk specifically about presentations. And I call this one how to make your presentation suck. And hopefully I'll do things that are really bad practices. And we'll talk about kind of triage it about why those things are bad. Okay. All right. Any other questions? No? All right. So this is some guidelines on sections of the presentation, 10 minutes. So you'll be handing in a video or recording of your presentation, as well as on the last day of finals at 11:59 seconds, you'll be handing in all of the final work. And I acknowledge, and I just want you to remember this point, please, that our presentation is on the 5th of May, but the last day of finals is on the 9th of May, right? So I don't expect you to be completely done the presentation. It's just the unfortunate reality that I don't choose when the finals are, right? If I had my way, I would have our final on the 9th. So when you're presenting, you're pretty much done. Okay. All right. Any other questions? No? All right. So let me exit this and let me go to the share for ensembles. And ensemble is the last thing that we'll talk about this semester because our focus on Monday is giving effective presentations. And so, let's see, slideshow, check. All right, that's still up. Nope, I don't want to just stop recording. Hide floating meeting controls. Let me blah, blah, blah. Okay. All right. I won't pause on the administrative slide. It's just the only thing I want to point to make about this. The 5th, 10:30 to 12:30 is presentations. That's our exam time. And then the 9th is our hand-in date. And it's all electronic as usual. Okay. So we talked about entropy, and I'm not going to go over, I like to kind of, tell a nice story and make it consistent. But I'm not going to go over the reminder for entropy. It's just my style that I usually do, as well as gain ratio. Okay. Now, of course, ensembles, that was the subject of my PhD thesis, and I can't believe I earned my PhD 15 years ago. The time flies by very quickly. But in human societies, when the decision is really, really important, they defer to the opinions of groups. So why do you think this is? Why do we do this in human societies? Why do we rely on groups? What do you think? Yes. Yeah. Okay. Okay. If some benevolent dictator just gets it wrong, right? It's kind of messed up, right? And for things like voting, choosing who's going to represent you as a municipality or a nation, or if you're enterprising to strip someone of their liberties, right? Throw them in jail. It's a really big deal. You don't want to get it wrong because an individual can get it wrong very, very often. If something happens on the street and you have a group of people and you ask 10 people what happened, you're going to get 10 dramatically, maybe some aren't, but you're going to get 10 differing opinions on what happened. So the idea that an individual is prone to errors in judgment is the whole reason why we defer to groups when it's really, really important. All right. And most things in human society, the important things, companies have boards, they rely on a group. Courts have juries, they rely on a group. Democracies, I almost said democracies have voters, right? So an individual can be incorrect, okay? And so the properties of group decisions are two different things. You get redundancy. And what that redundancy means is that the error prone actors are compensated for by the others in the group. You can tolerate some number of errors. Now, if you're dealing with a simple majority, well, you can tolerate floor of n over 2 many errors. That's pretty generous, okay? So you're more robust in the decision, okay? The other thing is that when you have different people in a group contributing to some judgment or outcome, these processes of arriving upon a mutually agreeable solution is very applicable to a wider variety of circumstances. So you get more agreeable solutions. You get solutions that apply well to multiple scenarios versus just one person's life experience. Does that make sense? Okay. And so this work stems from when I was a grad student. One of the things we worked with, and I'd never seen anything like that before at the time. We had a collaboration with a marine science lab, Bigelow Labs for Ocean Science in West Boothbay Harbor, Maine. And, the marine biologists, they weren't too happy with some goofy grad students saying we're counting sea critters. But the idea was we had an automated method for classification. So it's a supervised learning problem, classification of microaquatic organisms. And so this is primarily phytoplankton and zooplankton. And one thing I didn't know at the time is how important these things are. They're the foundation of the marine food chain. And so with the health of these phytoplankton and zooplankton goes the health of fish and other aquatic wildlife. They also trap carbon in their cycle and they drop down water columns and they act kind of like a dynamic blanket regulating the temperatures of the Earth's waterways. So they are the blanket of the Earth as well as a foundation of the marine food chain. And so the idea then is we were working with them, Bigelow Labs. They have an apparatus called the flow cam, and this thing siphons water directly from the ocean. So you have these exploration buoys, they're kind of floating out there in the ocean, and they have this flow cam device on it, siphoning water directly out of the ocean, and it sends back image data over telemetry over the cell phone network. And so here we see some pictures of various phytoplankton and zooplankton. I remember one of them is euphausids, and I used to know all this stuff much better 15 years ago. But we would process these images, each data point, as a vector valued instantiation of all sorts of things like the height, the shape, the texture, all sorts of different patterns. And so the goal then was to have an automated system that can discriminate and say, you are euphausids, you are species X, you are species Y. So-called counting critters, counting sea critters, which they didn't like at all. We thought it was funny. But anyways, the idea then was to build a system, supervised learning, that would effectively take an ocean census. Because if you can look at healthy population distributions, you can protect against and address and apply mitigations to these catastrophic algal blooms. If you want to kill off a waterway, you have an imbalance in the nutrients and you get a proliferation that's unnatural for algae. And they'll suck up all the oxygen and kill off every piece of marine life in that region. It's extremely catastrophic. So the idea then was to have an automated system that served as a kind of early alert that would give you a continual ocean census with respect to the microaquatic organisms population distributions. Does that make sense? So these data science issues are really, really powerful. And this is just a simple example from over 15 years ago of using many of the techniques that we've talked about for a problem in marine biology. And one of the neat things I think about data science and machine learning in general is that because you focus on the domain and the data quite a bit, and we saw that with the New York City taxi problem, you learn a lot about how other systems work and why they're important. And so forevermore, whenever I go fishing, I can never look at the ocean the same way, right? Because of this. Okay, so we have our typical supervised learning problem. We have our data set, and these were D-dimensional features, and our feature dimensionality ran in the hundreds to thousands, right? And that's very typical with a real valued problem, trafficking in things like imagery. Okay, and so we also had our ground truth, and so graduate students, PhDs in marine biology, would sit in a lab. You collect, and I've actually been on these cruises several times, would collect water from different depths in the so-called water column at different buoy locations. And they would collect water. So you have this chamber that is waterproof and water resistant, and you lower it to specific depths in various locations. You open it up, fills with water, you close it back, and you pull it back up, and you've collected water at different depths at different locations. And then they take this, prepare some slides, and they sit in the lab using their knowledge. Okay, this is Euphausis, this is Finmarchicus, this is whatever all the other names are that I forget. But nonetheless, you get your ground truth labeling. And then we take this data set and we built a bunch of classifiers. I'm happy to talk about it with you another time, but that's not the subject here. And so I just want to show you another example of using the same things that you've learned out in the wild. And so the result is from all of these feature vectors and ground truth labels is our label instance pairs that were used for our supervised learning problem. Now, this notation is a little bit different, and I really wanted to show it to you just to kind of make you aware that there are different ways of saying the same thing. And so we have our training set, our in-sample data. These are our label instance pairs. In bold, we have our vectors, and that's the tradition in mathematics and publishing. Vector value quantities are in bold. Sometimes you see the arrow on top of them. So we have our label instance pairs. Each label, Y1, Y2, Y3, etc., is the ground truth label associated with each of those vector instantiations. So we take our training set, we input it into a so-called classifier inducer, and we output an estimator, our G, final best hypothesis. It's really an approximation of this unknown target function. And so we use this hat over F to represent an estimator. It inputs vector quantities, X, and it's indexed by a parameter vector theta, because every decision tree, for example, has a particular set of nodes in some ordering that represents that best hypothesis. Does that make sense? Any questions? And so we input our in-sample data into a classifier inducer, and we get a function estimate that maps inputs X out of sample to label estimates or predictions Y hat. That's where the Y hat comes from in the Jupyter notebook that I demonstrated. So the idea behind this inducer, our learning model, is to reduce in-sample error, reduce the so-called training error. Does that make sense? Any questions? No. And so here, graphically, we have some geometry of our points in feature space. And in this case, we have two-way categorization. But in the phytoplankton problem, we had about 42 within the species that we did, but there are several hundreds out there. And there are some that they have never seen yet. And then we used to kind of quip when we were grad students, what if this thing discovered a new species? Who gets to publish it? Is it the system or is it the grad students? But anyways, so the idea then that instances within a category are more similar to one another for some definition of similar. And when we talked about clustering, we talked about distance from the center as being the litmus test of what your membership or what drives your membership. Those that are in different classes, categories, are less similar. But in the real world, the issue lies at the seams here. Now, very rarely do you have your groupings perfectly separated. You'll notice here, this region, there are instances that belong to class 1 that overlap with instances from class 2. This is often called the area of confusion. Because if you were to draw PLA, a linear model, or if you did your axis parallel splits, like a decision tree, there's no really good way to tease apart those in the confusion region. And that's typically where your classes, your groupings overlap with one another. And there are all sorts of methods, nonlinear methods that you can use to try to pull these apart. And the idea is you apply different transformations to try to change the geometry such that it's more amenable to be partitioned in a more reasonable way. Does that make sense? Any questions? No? And so what is an ensemble? An ensemble is for supervised learning. There's a regression equivalent that we won't talk about. But with an ensemble, you take your individual classifiers. So here we have our training set, and we have classifying inducer 1, 2, 3, up to size M. So you can think of this as a team of size M. Now, each one of these inputs the training set in some fashion, and it trains your classifier. So each one of these is a learning algorithm. And the result is some estimator F1 hat through FM hat. Now, each one of these estimators can input an out of sample point and give you a label estimate. But with an ensemble, you take the outputs from the individual so-called component classifiers, component, and you aggregate their outputs in a type of voting mechanism. And just like we talked about at the outset, something special happens when you have a group. Their decision is less error prone, but also it's more applicable because you have all of these potentially differing opinions. Does that make sense? Any questions? No? All right. And so the idea that combining estimates improves the quality of the output goes all the way back to the late 1700s. And I could never get that right. That's the late 18th century? Is that it? You say 18th and you subtract one and okay, thank you. I could never get that. I guess because you have the century, you're in the century, right? And you end it on the, anyways, I could never understand that. English is a funny language, but nonetheless, it goes back to the late 1800s, to get that right, from political science theory, the Condorcet jury theorem. And what it says jurors are neutral. Jurors, or those who are judging, just like component classifiers in an ensemble, their opinion is not based on the opinion of another juror. Now, we know now, tools of statistics, they're independent, okay? They're independent in their judgment. They're also independent in how they make mistakes, okay? A juror, by Condorcet jury theorem, is also competent. And what competency means that, yes, you can make mistakes, but over time, if you judge again and again and again some outcome, that you are correct more than you're incorrect relative to ground truth. Does that make sense? Okay. And so this jury of humans, let's define a probability, PI, and it's the probability that the ith juror is correct. Now, you notice here, I didn't say innocent or guilty, I said correct or incorrect. Do you coincide with ground truth or do you not? Now, with this, okay, this is a binary outcome, either correct or incorrect. And we have in a jury trial in US court system, 12 jurors, and we have these 12 jurors, each of which makes a binary decision. So you can model this as a binomial distribution. And if we want to look at the error of this jury, for a simple majority, we need at least ceiling of n over 2, where n is the size of the jury, to be in error for the ensemble to get it wrong. So we can model this error as a binomial distribution, and we sum it up for the simple error majority on through the overwhelming error majority. Does that make sense? Any questions? No? So this error for an ensemble, let's try this out. If the error rate for each juror was 20%, okay, that's pretty high, but if it were 20%, just for an ensemble of size 3, the error of the ensemble cuts down by half. So here, the majority opinion, this combination of these individuals, these individual members, just for size 3, we can cut the error in half from what the base error was for each person, each juror. So more expanding on what Condorcet jury theorem says, if the juries are incompetent, meaning they are not correct, if they are competent, that means their error is less than 0.5 for the binary decision. All right, they are correct more than they are incorrect. In the limit, as you increase the ensemble size, then the error of the ensemble goes to zero. You can derive it effectively to zero. If the jurors are not competent, meaning they are wrong more than they are right, that probability of error for binary decision is greater than 0.5. In the limit, as you increase the ensemble size, the ensemble, the error goes to one. They're wrong all the time. All right, so that talks about the competency of the juror. And if the jurors are perfectly on the fence, they're right and wrong the same amount, P is 0.5, you don't get any improvement afforded by the ensemble. Does that make sense? And so this is based on very rigorous theories that go way back to the late 18th century. Okay, so I plotted this out, this error, and we can see for US jury trial, right around a jury of 12 here, it's roughly, I can't go up very easily. It's right around 95%, right? And 95% is considered statistically assured. And so the reason why a US jury is 12 people is because they want to be statistically sound based on conjoined jury theorem. Does that make sense? So I've hopefully proven to you, theoretically, we'll see how that works in practice, that this idea of combining opinions of these supervised learners, these jurors, if you will, can reduce the error. And so one of the things you can do with ensembles, if you have a data problem and your data has a lot of overlapping regions, it has a lot of confusion, try taking your base model, putting it in an ensemble, and increasing the jury size. And you can get improvements in many cases. Does that make sense? All right. And so in human societies, and I'm going to have to continue the balance of this on Monday, for a jury to be incorrect, they have to share common biases. And when they do jury selection, and I remember being on jury in Delaware, I haven't been on one yet in Massachusetts, but it's your duty if you're a US citizen to be a juror, as well as voting. It's a very serious thing. The defense and the prosecution try to bias the selection of the juror. They want to have shared biases. They want to break this idea of neutral or independent jurors afforded by Condorcet jury theorem. Now, of course, the defense, they want to bias it in their direction, and the prosecution, they want to bias it in their direction. Now, in order to have good juries, you have to, bad juries, for them to be incorrect, you share common biases. And in human societies, they try to look at your composition, culture, socioeconomic status, and so forth. So if you say you're a college student in data science, they ain't going to pick you, right? You're too logical, right? They want someone who can be easily influenced by whatever statements they have to put out, okay? Now, of course, classifier juries don't have cultures, but they do have different aspects that can influence their decisions. And why won't this work? Hide, release the pen. Oh, the pen's over there. Okay. So the idea then in having a good ensemble is to build a classifier jury in a way that breaks these shared biases. How do you do this? Well, you have to look at all of the factors that influence the errors that these classifiers can make. And in the best case, the goal then to break these shared biases by making their errors as diverse as possible. Now, you can absolutely accomplish this with randomization. In my PhD thesis, the new method that I contributed was that you don't have to use randomization. In fact, randomization can work very poorly. You want to space these distributions apart equidistant from one another. And if you have a certain way of spacing them apart, and you can spread them out, separate them as far apart from one another, every single time you can do better than you can just by relying on randomization, right? And that got me my degree. Anyways, so let's look at how ways that existing approaches, popular approaches, for how you break these shared biases. Now, when we look at what goes into a classifier, we have the instances, the training instances. Yes, we've been talking about your in-sample data, but you don't have to choose every single data point. You can choose from a random sample of some sort from your training examples and input that to your learner, okay? You also have the feature set representation. You don't have to measure the texture of an image in a certain way. You don't have to measure annual salary. You could measure something else. So the choice of feature set changes the geometry of the data points. And if you change the geometry of the data points, you also change the way the errors play out for the resulting learner. Does that make sense? Okay. The other one is the induction algorithm. You can change the way your learning algorithm searches through feature space. One, you can have jump around randomly. The other, you can have sort of a wiggly path that's very smooth and all sorts of variations between. Because the choice of how you search through features, excuse me, the choice of how you search through hypothesis, the space of hypotheses, also impacts your resulting classifier's error, the so-called regularization sequence. Then, of course, the parameter vectors you use. Different instantiations you found for the normal IID model or Poisson changes how this thing fits. You can wiggle things a little bit. And then, of course, you can do things with the class label. So we'll focus in this class over the next minute or two on the instance selection, how you can change the instance selection, because as we talked about, when, for example, in PLA, you do that weight update, W gets W plus our learning rate, YI, XI, right? We talked about this idea, minus, 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 plus, 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 this idea of starting with a decision boundary and moving that decision boundary in some way when you make that new selection. And so if you select different instances, subsets within your in-sample data with which to train your learner, you're going to have this line come to rest in different ways if it doesn't include this one or doesn't include that one. Does that make sense? Any questions? No? All right. So there are two methods, and we'll end with this. You can do it by sampling or by direction, by bias sampling. The most popular method for doing this by sampling is called bagging, and the most popular method for doing it by biased or directed sampling, achieving this so-called error diversity, is by something called boosting or add a boost. Does that make sense? Okay, so we will stop there, ending on time, and I will see you all on Monday, our last class. And we will finish the balance of this, show the Jupyter Notebook, and then talk about giving good presentations. Have a great weekend, and I'll see you all on Monday.